Welcome, everyone. Today we're going to be looking at the derivative. Now, obviously, we're going to keep talking about derivatives, but the derivative as a rate of change. So we're going to start to see we've learned some basic derivative rules at this point, and now we're going to see kind of the basic interpretation of our derivative, how we're going to think of it in a lot of contexts. And it has to do with what we call the average rate of change. So we have a function, and we're kind of interested in how fast that function changes. And so we have this gadget which we call the average rate of change of our function. So it's describing kind of how fast our function changes on average over some interval of x values, in this case a to b. And the way we define this average rate of change is it's the change in our output of our function versus the change in our inputs. And we've seen this thing a bunch of times already. We're going to keep doing it. This is our slope formula. So this is just the change in y over change in x, essentially. And this is really, this slope formula, this describes kind of how fast the output of our function changes as our input changes as well. So graphically, we've seen this average rate of change before when we talked about the slope of a secant line. So if we had a curve, this was our function f of x, and then we had 2 points on that curve, point P and point Q. Well, if point P had coordinates a comma f of a, and point Q had coordinates b comma f of b, and we know the y coordinate is just whatever the function value is there, well then this average rate of change is just the slope of this secant line. And so when we talk about the average rate of change, what we're really doing is we're talking about, well, how much does the output of our function change going from one point to the other? So essentially the change in the kind of the vertical height, versus how much does our input change over that same progression going from one point to the other. So we're looking at the change in our output versus the change in our input. And that's precisely just the slope. And so this average rate of change it's telling us on average how much are we changing over this x interval where we go from x equals a to x equals b. So over this interval, on average, how much does our function change per unit of x? So there might be parts of this interval where the function kind of changes slowly. So maybe right in here it's not the function isn't changing as fast, but then over here it's changing much faster. But on average, what we're doing is we're kind of averaging out those differences. So we're taking, some of the slower changes, we're taking some of the faster changes here, and we're saying, well, this is the average change. And it's really just the slope of our secant line. And so we can calculate, if we had a function and we were interested in some time, or I say time intervals because we're going to be talking about time intervals, but not yet. We're looking at x values here. So just in general here, the average rate of change. Let's try this example. Let's see how this works. And we've done this kind of thing before. Now we're just putting a slight different spin on it. We're looking at the function x squared in this example, and we're looking at some different intervals for x, and we want to calculate the average rate of change. And the way we can do that is just by using that slope formula. So let's look at this average rate of change for our interval from 1 to 2. And the formula says it's the difference of our output values. So we take the 2x values at the inputs here, at the endpoints here for our interval, or if we write it as an interval, we can just take the two endpoints there. We plug them into our function, and then we subtract. And then we keep the same order in the denominator. So 2 and then 1. So we do 2 minus 1 down there. If we actually plug the values in, when we plug 2 into our function, we're just going to our regular function here, x squared. And we get 2 squared minus 1 squared over, well, 2 minus 1 is just 1. And then if we calculate, we get 4 minus 1 over 1, which is just 3. All right, so that's our average rate of change. And, you know, we can, if you want to throw some units on, it might be helpful to think of having some units here. So what's going on is our output changes 3 units per unit change in x. So we're going to be looking at some more examples where there's actually going to be, you know, real units that we consider. But for right now, it might be helpful to think of this. It's not just a number. We want to think of it ultimately as there are some kind of units behind here. So it's how much change we're experiencing, units in y, in the y direction, per unit change in x. All right, well, let's try another example here where or another interval, same function, different interval. So we're going to look at the average rate of change over this interval from 1 to 1.1. All right, so same function, but now we're just shrinking that interval down. Well, let's see what happens. So same setup here. We're going to plug in the right endpoint first, and then we'll put that same x value in the denominator there. Then we subtract and subtract off the other endpoint. When we plug in, we get 1.1 squared minus 1 squared over 1.1 minus 1, which ends up being 1.21 minus 1 over 0.1. And if we do the arithmetic here, this ends up being 2.1. And again, there are some kind of units there. So this is telling us how much our y value is changing per unit change in x. All right, so let's just shrink the interval just a little bit more. And let's look at the average rate of change. We're just shrinking it down over the interval from 1 to 1.01. And same deal. We're going to plug into our function. So we'll plug 1.01 in first. Then we'll plug 1 in and subtract. So we'll keep the same order for the denominator. And we're just calculating the average value. And this is just the slope formula, regular slope formula. When we plug in, we get 1.01 squared minus 1 squared over 1.01 minus 1 squared. We do the arithmetic, and we end up with 1.0201 when we square that decimal, minus 1 over, no squared there. Let's get rid of that. It should just be a 1. So these should just be the x values down here. Same thing here. What's going on? Should just be a 1. And when we do the subtraction, we're going to end up with 0.01. And let's scroll up there. And we clean it up, simplify, we end up with 2.01. And so when we look at these kind of values, as we shrink this interval, so notice we're shrinking this interval. We're going from an interval 1 to 2. Then in the next one, we've gotten much closer to 1. We're looking at the interval from 1 to 1.1. And we see that our average rate of change has gone down. And that kind of makes sense because it should, we're averaging, or it should seem plausible, because if we're looking at this larger interval, we're just averaging more things together. And so it seems plausible that the value could be higher, or it could be lower. But as soon as we start shrinking this thing down, we notice that the values all start looking pretty similar. So if we shrink it down even more, shrink this interval down so that we're kind of really looking really close to this endpoint 1. We're just slightly shifting to the right a little bit. And we have this really small interval here. Well, then our average rate of change is this 2.01. And these values are starting to look very similar. And it looks like if we were to keep this going, it looks like they're going to start approaching some common value. And that's ultimately what the derivative is. So the derivative, what we've been calculating, f prime of a, what it does is it measures the instantaneous rate of change of our function directly at x equals a. So it tells us how much our function is changing directly at that x value. And so really what we're doing with the derivative is we're doing the limit as b approaches a of the average rate of change of our function over the interval from a to b. And so what we're doing is we're calculating really what we have when we calculate a derivative is we're looking at the average rate of change of our function over some interval, and then we watch what happens as that interval shrinks down and gets closer and closer to one of the endpoints. And so we saw that, and this gives us then the instantaneous velocity, or instantaneous rate of change. So for instance, in the examples we were just looking at, we found that for the function f of x equal to x squared, over the time interval, or over the x interval from 1 to 1 or 1 to 2, we found the average rate of change was 3. Then over a smaller interval going from 1 to 1.1, we found the average rate of change was 2.1. And then over the interval from 1 to 1.01, we found the average rate of change was 2.01. And so if we were to kind of keep these intervals shrinking, keep them shrinking, what we would see is that these values end up getting closer and closer to some specific number. And that number, if we calculate the derivative of x squared, 2x, and then we evaluate at x equals 1, because that's the kind of the interval where or that's the endpoint of our interval where we're kind of shrinking down towards. We're getting closer, these intervals are all getting closer and closer to that one endpoint. Well, if we evaluate this derivative at x equals 1, what we end up with is 2. And so as these average rates of change, as our intervals shrink down, the average rate of change, well, we're averaging kind of fewer things together. And so as we read down the table, as we calculate these average rates of change, they get closer and closer to our instantaneous rate of change. And this is the kind of the idea, is the slope formula in general allows us to talk about how much our function changes, the kind of how fast it changes on average. And then kind of going that extra step of doing a limit and watching what happens as those intervals shrink down, well, that's going to give us kind of the instantaneous, what's going on directly at x equals a. How fast is our function changing directly at that one specific point? And that's what we're investigating when we talk about a derivative. So let's, well, we just did it. Let's calculate that instantaneous rate of change. And so a lot of times we don't say the word instantaneous, we just say rate of change. We'll specify average rate of change, but in general, sometimes we leave off that word instantaneous. So if we just saw this problem, calculate the rate of change of our function x squared at x equals 1, well, we would calculate the derivative. So 2x. And then we'd evaluate. And so we plug in 1. So we get 2 times 1, which is 2. And that that's our instantaneous or just rate of change. And it's going to be helpful to kind of think of this. It's not just a number. There's normally we want to think of it as there's kind of units behind. So what this is telling us is this is the units of y per unit change in x. And so we're going to see in example 3 here, and I think we'll save this one for class, but we're going to see that we have a function here, and we're going to calculate the average rate of change. We're going to calculate the instantaneous rate of change. And the way we're going to do this is, or the result once we do this is going to have units. And so our units here are going to be for population and for time. And so we're really going to see kind of the rate of change. It really involves units in a lot of cases. And so we're going to look at example 3 in class. So we'll see you then.